talking about. Seattle is a cross-platform piece of software, so it runs on PCs, but also on Raspberry Pis, smartphones. And then we thought it would be a good idea to port it to routers too. So at its core, there's a sandbox. This is a restricted Python environment, so you get high level, but still general purpose programmability. And these sandboxes are resource isolated and safe, so to say, in some sense of the word, so that you can let even untrusted researchers or experimenters run code in these sandboxes and not be afraid that anything bad happens. The sandboxes can be remote controlled. I think it makes sense for a testbed where you don't necessarily have the device in your hands to allow this. And since it can do TCP and UDP, you can also run distributed services on top of it, or small servers, or distribute computation, stuff like this. So these are the components that Seattle Testbed consists of. I'd like to start at the top left. So the first larger box around this would be a device. For instance, my laptop here, which runs our software, contains a node manager. This is the network interface for experimenters to interface with and send their commands. And then there's a couple of sandboxes. They might belong to different people, to different researchers. So there are keys identifying who is allowed to access what sandbox. Since I mentioned experimenters, these are the guys on the bottom. So there might be many experimenters interfacing with many devices that in turn run many sandboxes. And they use a small program to do that. This is like a shell-like interface so that you can upload data and code and start it and stop it, query the status and so on. These are actually the most important parts already. So you can be the experimenter yourself. You can run the sandboxes on your device right away. And then you'll have a small experiment setup where you can use our API already. In a larger sort of operator-like setup, you could have someone that runs a clearinghouse as a trusted intermediary, and then you register the sandboxes there, and the experimenters also register there. And the clearinghouse is the point where this exchange happens so that experimenters get assigned to sandboxes. But you don't need to have this, and you could even run your own if you like, so you can take all of these components, modify them as you wish, run as you like, and even be reusing stuff that we have. For instance, the lookup service. If you happen to fork from our code base, then you could still use our lookup service or our package builder and all of this. A possible deployment looks something like this, and this is actually how the experiments that I'll be talking about were created. So you would have a router at the center where our software runs on, and then all of your home devices just connect to that router. Or this, by the way, looks very similar to what the Bismarck project is doing, or Sam knows, if you've probably heard that name. They are doing network measurements mostly in an architecture that's very similar to that. So you replace your own router by a box that they provide. So the thing that we could also do is just use a smaller router that doesn't see all of the traffic in the network, and just use it as yet another host on the same network. And I guess a few of you know RIPE-Atlas. These are these small little USB-powered devices that are network probes. So you could deploy Seattle on a Wi-Fi router similar to that. Here are a few obstacles that we met when we ported our software. Most of these will not come as surprises to you, but as indicated, we were probably coming from the other direction. So we had our software running on PCs and on smartphones and Raspberry Pis, and then we just ported to the routers. So we were coming from rather powerful devices with large memory, lots of storage, to these relatively tiny boxes. And this was one of the obvious things that we ran into. So if there's not much memory that you can use, if there's not much flash, then you really need to think hard before you do crazy things like using the fork syscall. Otherwise, it will just start eating away your memory, and at some point, either you're dead in terms of your router sadly doesn't work right now and you have to reboot it, or it's just that your process gets killed and then you have nothing out of it anyway. Another thing is, since our system is based on Python, there are a few tricks that you can use. So for instance, you don't want to cache the Python compiled bytecode files. The software that we have, the sandbox and node manager and so on, they use a few components that are identical but spread across different directories, and in order to save some space, you can just create links, well, obviously. And finally, we would use an extrude and also add swap space so that we could reduce the memory back pressure a little and have a working system. Experiment setup, there's nothing too fancy about it. My colleague had a TP-Link WDR 3600, and this has a CPU and a little bit of flash and a little bit of RAM and 2.4 and 5 gigahertz Wi-Fi interfaces. And he did his experiments in New York City, and he had a setup at home and a setup at a university. The stuff that he added to the sandbox, well, the sandbox that I was talking about has an API that's relatively generic and lets you do a couple of things like use threading, randomness, and TCP and UDP and stuff like this. But he also extended it so that you could run ping and traceroute and two things that Claudio would probably not approve because yes, we are just grabbing through the output of IW and the IP tool and try to find values that are interesting for us so that we can output them. So we are basically breaking not your rule but your suggestion to use proper interfaces for this stuff. We did it like this because we're integrating on a relatively high level. So for the things we did, we were okay, but we also understand that this is not the bestest of designs. Sorry? Yes, that's what we're doing. We take the output of the program directly and then parse it and then supply it over our API to a small Python program, which is the experiment. Okay, other things that we are doing. Well, if you do a Wi-Fi scan, then it makes sense to sort of obfuscate the Wi-Fi MAC addresses that you see. At least if you really want to tell your parents and friends to have this installed on their routers, then it's probably nice to not break their privacy in terrible ways. And also we have some kind of software firewall where we just don't allow packets to private IP addresses so that an experiment can, just start printing stuff on a network printer or things like that. So this is already the results section of my talk. I have a few CDFs, cumulative distribution functions, that all look similar to this. And the way you would read this is that on the y-axis you look for a percentage, say 40% or 20%, and then you'd say, okay, for 20% of the flows that we saw in the 5 gigahertz band, the channel utilization is 10% or less, and I would do it like this. So this is how you read this graph, basically. Start on the y-axis, go to the right, and once you hit the graph that's put here, you just go down and read off the value. And what you can see is that the channel utilization at the place that Shuafang measured, and for the time of his experiment, obviously, was much lower for the 5 gigahertz band than for the 2.4 gigahertz band. We also had this experiment where we tried to download stuff from a local node, and this also works better for the 5 gigahertz band. For instance, if you take the 80% percentile, the 80th percentile, then this is lower for the 2.4 gigahertz band than for the 5 gigahertz band. So the thick green line extends further to the right, which basically means better performance in this case. There are situations where using the 5 gigahertz band at that specific point obviously doesn't help you very much. This is an experiment where we just checked the latency to a node on the same local area network. And as you can see, there's not much going on here. So it doesn't really matter if you use that band or the other. And for retries, there's also this nice little figure. So this is all stuff that you can basically query from the Wi-Fi interfaces, and there's much less retries for the 5 gigahertz band. And as you can probably see, or interpret from what I say already, we're measuring really only at one point. So all of the things that we see here should not be taken to be something that's generally true or will be true wherever you are and for all use cases and bands and so on. But this is really just showing the possible results that you can generate relatively high-level software. And this is just more statistics from the Wi-Fi interface. So this shows that there's times when the interface is seen as busy, which not necessarily overlap all the time with when the interface receives something. And there's almost always some transmission going on, as you can see, but it doesn't really add too much of a, it doesn't add too much, basically. And I'm almost done already. Well, that's turning out pretty nice. So the 2 blocks of things that I wanted to mention was porting our existing software that runs fine on PCs and smartphones and devices like this to OpenWRT was relatively challenging because of the constrained environment, and a few things are different from what you would expect them on a normal Linux box. Stuff like not having user management, for instance. It's not that we depend on this, but you sort of come to expect it and then you're surprised when it's not there. But it was also pretty rewarding and good fun, and we learned a lot by this. And I think the takeaway point for us was everything is so small. It really feels tiny, and you feel pushed back by 20 years to the devices that you used well back then, where you always had to think about not using too much storage because you couldn't afford another hard drive and so on. And for the actual software that we wrote, I just want to reiterate that these are reusable components, so you could run them almost on any platform that you have, and you don't need to take all of the stuff that we have, but you could choose whatever you like and use it and repurpose it for whatever what you do. This is cross-platform software, as indicated, so shouldn't matter too much on what platform you want to run it. And since it's free and open source software, take it, use it, sample requests, send issues. Well, you know how it works. And that's all already. And in case you're interested in my BGP key fingerprint, well, this is it. Thanks.
Are there questions from the audience?
I'm also fine to take remarks from people that know better than me, because we just built all this and then discovered a lot. So if there is something in your mind where you think that we could even improve, please let me know.
Okay. Seems we're good.
Okay, thanks for your patience.
Thanks, Albert. So next talk is scheduled actually 3:30, but now we are over to Harris again.